All right, welcome to this explainer. Today, we're diving straight into Charles Proxy to really master the art of mobile traffic interception. Look, if you're an IT support engineer dealing with mobile apps, you already know that trying to resolve user issues can sometimes feel like trying to put together a thousand-piece puzzle in the dark. It's incredibly frustrating. But today we are going to flip the lights on.
You know that feeling when an app is just spinning or it crashes and you're left staring at a completely useless generic error message? That's blind debugging. Without a proxy, you're entirely relying on those vague UI errors and basically just making educated guesses. But look at the contrast here. When you have full visibility, it's literally like having X-ray vision for your network. You transform from a guesser into a master diagnostician because you can see the exact API failure, the headers, the exact payloads, and the raw status codes.
So here's our game plan for this explainer. First, we'll look at the black box. 2 will be equipping the X-ray glasses. 3, reading the bones. 4, playing God. And finally, 5, the boss fight, where we'll actually fix a 401 error.
All right, part one, the black box, and exactly why network interception matters so much in the first place. Whenever an app fails with one of those generic errors, we're dealing with a black box. To look under the hood, we use Charles Proxy, which acts as a secure man in the middle. It's just an application running on your computer that sits right between your test device, like an iPhone or an Android, connected to your Wi-Fi, and the rest of the internet. It intercepts, inspects, and decrypts the entire conversation between the mobile app and the backend servers, all in real time.
Moving right along to section 2, equipping those X-ray glasses. Let's talk setup, proxies, and certificates.
Okay, the first big hurdle is simply getting your mobile device to route all of its traffic through your computer running Charles. It's actually super easy. First, you just grab your computer's local IP address from the Charles Help menu. Then you grab your test device, go into the Wi-Fi settings, flip the proxy to manual, enter that IP address, and set the port to the default, which is 8888. As soon as you do that, Charles will pop up a little prompt on your computer asking if you want to allow the connection. Click Allow, and boom, the bridge is built. But here's the catch. Just routing the traffic isn't enough anymore because practically all modern traffic is locked down with HTTPS encryption. To actually read that encrypted data on, say, an iOS device, you have to install the Charles root certificate. You just open Safari on your phone, browse to chls.pro/SSL, and download the profile. But here's the vital step that absolutely everyone forgets. You have to go into your iOS settings under General, then About, and explicitly enable full trust for that certificate. If you don't enable full trust, the traffic is just going to stay completely scrambled.
Now, if you're on Android, things are a bit different, and it really brilliantly illustrates Android's secure by default architecture, especially on Android 7.0 and up. You can't just install a certificate on the phone and expect it to magically work for every app. You actually have to add a specific network security config XML file directly to your app's codebase and then update the Android manifest so it knows to trust user certificates. Practically speaking, this means out of the box, you're usually going to be intercepting debug or test builds of your Android app rather than the fully locked down production version you'd get from the App Store. Which brings us to section 3, reading the bones. Let's dissect some actual HTTPS requests and responses. So traffic is flowing, SSL proxying is enabled, and now we can really look at the anatomical structure of these network calls. Charles organizes all this data really cleanly into tabs. The Overview tab gives you the 10,000-foot view, connection status, HTTP response codes, timing, all that good stuff. The Request tab shows exactly what the app asked for. This is where you're going to hunt down outbound HTTP headers and authorization tokens. And finally, the Response tab shows you exactly what the server answered with. That's where your JSON payloads and your API errors are going to live. Next up is section 4. I like to call this one Playing God, because we are going to modify traffic using rewrites.
See, Charles isn't just a passive observer sitting on the sidelines. You can actively alter the traffic to simulate crazy error conditions, and you can do it without touching a single line of backend code. You basically have two main weapons for this. Breakpoints let you do manual, on-the-fly edits. You literally pause a request in midair and type in changes. The rewrite tool, on the other hand, is for automated, completely hands-off modifications based on specific rules you set up beforehand.
But this brings us to a massive challenge with modern debugging. As you can see from this quote, apps today are impatient. They have really aggressive 5 to 10 second timeouts. So breakpoints can be incredibly tricky. If you pause a request to manually edit a JSON payload, and it takes you, say, 12 seconds to physically type it out, by the time you hit send, the mobile app has probably already crashed or thrown a generic timeout error on the screen.
And that is exactly why the rewrite tool is your best friend. It is so much safer for complex debugging because it's instantaneous. By creating rewrite rules, you can consistently reproduce tricky edge cases. You can automatically force a 429 too many requests status code to simulate a thundering herd and see how the app handles rate limiting. You can force a 500 internal server error, inject missing headers like an X device ID, or even scramble JSON strings just to see if the UI gracefully handles the bad data or if it totally crashes. All right, it's time for Section 5, the boss fight. Let's walk through a real-world scenario and actually fix a 401 error.
Picture this. An IT ticket hits your desk. A user's app is just showing a blank screen with a super helpful "something went wrong" message instead of loading their data profile. Without Charles, we're just guessing. But we've got our Wi-Fi test device connected to Charles, we retrace the user's steps, and immediately, right there in the sequence view, a specific API request flashes red. So we click on that red request, open up the Contents tab, look at the response, and boom. Right there in the raw JSON data, it clearly says error, token_expired, with a status of 401 unauthorized. No more guessing, we have concrete proof that the server is explicitly rejecting the call.
But wait, why is it expired? If we flip over to the Request Headers tab for that exact same network call, we can capture the actual JWT authorization token the mobile app tried to send. Inspecting this reveals the real culprit. The app's internal token refresh logic totally failed. It sent an old token to the server instead of requesting a fresh one.
Now, instead of going to the dev team and saying, hey, the screen is blank, please fix, you can hand them an absolutely bulletproof bug report. You can export a .chls session file right from Charles and attach it to the ticket. It acts exactly like an airplane's flight recorder. You hand the developers the exact failing endpoint, you highlight the expired authorization header for them, and you provide the exact JSON error response. You've just transformed a completely vague user complaint into a precise, actionable fix. Okay, before we wrap up this explainer, I have a massive public service announcement. Please remember your post-debugging cleanup. If you just yank your phone's cable from your computer but leave the manual Wi-Fi proxy enabled in your phone settings, your phone is going to endlessly search for Charles. You'll be walking around all day staring at confusing, no internet errors on your device. Always revert your Wi-Fi settings, turn off SSL proxying in Charles to save some CPU, and remove those test certificates. To cap off this explainer, I want to leave you with a bit of a provocative question. If it's this easy for us to expose and rewrite hidden mobile traffic using a proxy, what undocumented shadow APIs or extra data payloads are leaking out of your production environment right now without you even knowing? Having full network transparency isn't just about fixing annoying bugs. It really is the ultimate superpower for securing and truly understanding your entire ecosystem. Thanks so much for joining me on this explainer, and happy debugging.